This is an introduction to harmonic motion and specifically simple harmonic motion. Simple harmonic motion is a special case of harmonic motion, and that's really what we're going to discuss. Actual harmonic motion is a little bit more complicated and requires some pretty intense math at times. So we'll talk about what harmonic motion is, and I'll kind of give you some basic stuff that you need to continue on and talk a little bit more about harmonic motion, how to approach it mathematically, and how it affects physics. So harmonic motion, there are a couple things about it. It's periodic. It repeats over some period of time, t. And when this happens, you have an object that will start at position P. It will go through some equilibrium position, and it will reach a maximum position, which we'll call Q. And then it will go back, turn around, and head to P. And it will keep going this way over and over again for as long as it can. Some examples of harmonic motion are things like springs and masses. If you remember when we did some labs, we would pull a spring. Well, actually, we didn't get a chance to do this one. You could pull a spring down, hang it from the ceiling, pull the spring down, and let it oscillate up and down. That's kind of like simple harmonic motion. You could take a spring, place a mass on one end, and attach the other end to a wall, compress it or stretch it, and let it oscillate back and forth between the maximum and minimum amplitudes. And those would be a harmonic oscillator as well. But also pendulums. And if you think about it, really the seasons, if you start off in it's cold winter, it gets warmer in spring, it gets hot in summer, it gets cooled off in fall, and then it gets cold again in winter. And that just keeps repeating itself over and over again. So in a lot of ways, the seasons, or dictated by the motion of the earth around the sun, are going to be harmonic oscillators. The same thing with the rotation of the earth about its axis. When you talk about the sun at noon, it's at the highest point in the sky. And if you go to noon the next day, or at least a solar noon the next day, the sun will also be in the highest point in the sky. And so because of this repeated behavior of the sun's position, the days are also a harmonic oscillator. But there's more to it than just that. There's, say, timing belts on cars. If you watch NASCAR races, they go around in a circle. You start at the starting line. That's also the finishing line on the other side. And so that is a harmonic oscillator in a sense. Photons, electromagnetic waves, even the water cycle for the planet Earth could be described in some way, shape, or form as a harmonic oscillator. So it is a really fundamental thing that we're talking about for both nature, and it's also the foundation for a lot of higher physics, especially things like quantum mechanics and particle physics. So there are a few assumptions that we have to make when we talk about simple harmonic oscillations. One of those assumptions is that the system is conservative. So we're specifically talking about simple harmonic oscillators. All harmonic oscillators are not necessarily conservative, but for the harmonic oscillators we will consider, the simple SHOs, simple harmonic oscillators, those will all be conservative. So that is our first assumption. And the result of this assumption is that the oscillations will not decay. They will always go between some minimum through an equilibrium point to a maximum, back through equilibrium, back to minimum, and it will keep repeating that way forever unless the system is disturbed. The oscillations will also will start between at some maximum and go to a minimum, or they will start at a minimum and they will go to a maximum, but they will never be smaller than that minimum. They will never get larger than that maximum either. So has to do with conservation of energy. If you start off, you put a certain amount of energy into the spring at some position, it will convert that energy, that spring potential energy, into kinetic. That kinetic energy will get converted back into spring potential energy, and it will never increase. That total energy of that system can never increase because this is a conservative system. Another assumption we have to make is that for springs and pendulums, the mass of the spring, or I guess the string for a pendulum, or sometimes a rod, those will all be significantly smaller than the mass of the oscillator. So what I mean by that is, for example, here's a diagram. If we have a wall, we attach a spring to it and we compress it some distance, and we'll call this distance P. And somewhere in the middle is our equilibrium position, 0. And then we have a position Q, which is our maximum. And we'll give it a direction as well. We'll say positive X is to the right. So if I have the spring compressed and I let this thing go, it's going to oscillate between P and Q forever. This is assuming that this is a conservative system, which means no friction, right? So no friction is an important part of this. And for a spring system, it means no friction where the block is in contact with the surface. But for a pendulum, it means that there's no friction in the pivot point. Um, but yeah, these are the two main assumptions that we have to make when it comes to talking about simple harmonic oscillators. There's another thing that's kind of important. We'll say number 3, and that is the force that's exerted to cause the motion. That force that's exerted is going to be proportional to displacement from equilibrium. So that's not really something you need to really be concerned about, especially not for the AP exam. But it is an important assumption that we make, and we'll see why in the future, in one of the future videos. There are a couple other things I want to talk about before I end this video. The first one is, well, they're all definitions. So I do want to talk about a couple of definitions before this video is over. So let's get to that. The first definition that I have is this idea of an amplitude. So an amplitude is this maximum displacement from an equilibrium position. And that doesn't mean that it's from the minimum of the bottom of a sinusoidal function to the top of the function. It means it's from the 0 point, the middle of the function, to the top or the bottom, right? Because we're talking about displacement, which means that if it goes up or if it goes down, it's going the same amount of distance. So that's kind of a real big part of this. And we haven't really talked about amplitude very much in this class because we haven't really had a need to. We haven't talked about the sinusoidal or sine and cosine nature of these functions. But now that we are about to do that, amplitude becomes a pretty important thing. The second one, or the second definition, is our period of oscillation. You know what a period is. I called it like a period of rotation or something like that, but is basically the amount of time that it takes to go through one full oscillation. That is, it takes from, in our example, to go from the starting point, point P, through the equilibrium position to point Q, back through the equilibrium position, and finally ending at point P again. So it's always going to go in this order, and start, equilibrium, maximum, back to equilibrium, back to start. Another definition is restorative force. This isn't something that we've really hammered on very much, but if you kind of maybe recall the 1 or 2 times I mentioned it back in our discussion on Newton's laws and Hooke's law, we talked about the spring force was a restorative force, and a restorative force is any force that will act to restore some system to an equilibrium position. And that affects our spring system specifically in a number of ways. So if I have a spring and a mass attached to it, and I start off at point P, and I draw a force vector, the force is going to be pointed to the right. And that force is going to cause this mass to accelerate, right? F equals ma, Newton's second law. But eventually, this block is going to reach this equilibrium position at x equals 0. And we call the equilibrium position 0 for a very good reason. And that reason is because once this block reaches that position, then you are no longer at a, you no longer have a spring force. The spring force at this time is 0 because you are at the natural length of the spring. And since the spring's natural length, at the spring's natural length, the spring will not exert any sort of force, which means that our force will be 0 again, and which means our acceleration will be 0. However, it still has momentum because it was moving as it passed through that position, and so it's going to continue to move past the equilibrium point. And where it will go, ultimately, is to that position Q. So once it is at position Q, then, or once it passes the equilibrium position, I guess, then the spring is going to start to exert a force in the opposite direction until it reaches a point where it can accelerate the mass to 0, or 0 velocity. It will turn around and the block will start to move backwards and increase, and now it will have a negative velocity. You'll have a negative velocity. It will cross through the x equals 0 point, the equilibrium point, and the spring force will then turn around again and start to push backwards, and it will cause it to accelerate in the opposite direction, which will cause that negative velocity to go to 0. Eventually you'll be at 0, you'll be at position P, the force will start to push it back again, and that's why we have a harmonic oscillator for this. A similar type of thing would happen with a pendulum, where you'd have both kind of a combined gravity and tension force acting um, to keep it horizontally moving, and then to move it up and down along this kind of circular path as it oscillates back and forth between the left side and the right side of the motion. Um, and again, you will see that the force is 0 at the bottom of a pendulum. You will see that the force is at its maximum on either end of the pendulum swinging, and also you will see that the velocity is 0 at the ends, and the velocity is maximum at the equilibrium position, because all of that spring or gravity or whatever energy has been converted into kinetic energy when you are at equilibrium position. So the equilibrium position, the reason why we call it x equals 0 is because all of our potential energies are dependent on position. And so if you're at this equilibrium position, you have no potential energy. All of your energy is in kinetic energy. If you're at the maximum, you have no kinetic energy. All of your energy has been converted to a potential energy of some kind, and it'll just keep going back and forth like that forever. So these are the basic concepts I want to talk about to get ready for the next stuff, which will be a little bit more mathy. So prepare for that. But I will post the video of that shortly. So until next time, we will see you.